Hi everyone, this is the videos for tutorial 7. This is the last video before the quiz. I'm going to give you a little bit of information regarding that. I don't know yet if there's going to be a review session. If we do have one, it'll probably be next Tuesday. I believe your exam is on Friday, so that'll be enough time to study, I believe, between the exams. But we'll see how it works. I think Monday would actually be a little bit better in some sense, but I don't know how important the stuff we go over on Tuesday will be. And yeah, I believe it's better to have the review session after the last lecture before the exam. But we'll see what happens. I'll do the same setup as I did for tutorial 5. If you bring me your quiz before it's due, I will grade it for you and hand it back to you. Probably on Monday. So if you bring it to me on Monday, I will grade it, hand it back to you right away. You can take and study off of it. I don't know when the solutions will be posted. Probably be sometime Wednesday. But yeah, if you want your homework back on Monday to study off of, I believe last time people who brought their homework early, I checked it for them before I graded it, so you basically got full credit if you brought it in early. Because I could correct it, I tell you what you did wrong and you've changed it, and I grade the corrections and you get full score. But yeah, okay, so the problems you're doing now, virtual work, moment area, you're using the same setups as you did before. I don't know if these problems probably look very familiar to you. These 3 problems. But anyway, I'm not gonna... Okay, let's see what I can do. The first problem is asking you to find the slope left of the hinge. Some people are asking, well, what is the slope at the hinge itself? The slope at the hinge has 2 values. You have a slope on the left and a slope on the right. It doesn't make sense to say what is the slope at the hinge. You have to say what is the relative slope, like what is the difference in the slope between the 2 sides, or what is the slope on one particular side. It doesn't. You can't assign the hinge a specific slope. I want you to keep that in mind. That's why you specify 2 left. Anyway, the problem, it follows the same. The first 2 steps are always the same. As usual, you want to find your reactions, and then you want to get your moment diagrams. I'm not going to give you the moment diagrams. I believe at this point you should be comfortable getting your moment diagrams. And if you're not, please see one of us. Because I don't see how you can do well in the exam if you don't know how to get your moment diagrams. So yes, first that is that. Okay. The professor's been using some notation that might be a little bit confusing for some of you. For example, he uses this TBA notation a lot, and all this is the moment of the area, the moment of your moment divided by EI from A to B at point B. Now, what does this mean? Let's look at this expression. What does this actually mean? What does the area under your moment diagram tell you? The moment of your area under your area diagram is basically the integral, right? Another way of saying this is just this part. It doesn't include the moment part. The moment part as another term, but the area underneath the area of your moment diagram from A to B is the same as saying the integral from A to B of m over EI. But yeah, I just want to make sure that that's clear. So I don't want you to think that these are different concepts. It's just another way of using calculus, really, to solve the problem. Okay, all right, we have that. Let's look at our original problem. We have a roller, we have a hinge, we have a point mode, and we have a roller. Okay, we want to find the slope at this point. We want to find the slope here. Now, normally, before you were working with the cantilever, I believe, and the cantilever has a zero slope at the beginning. Here, however, we have a non-zero slope here. I'll sketch the deflected shape for you, just so that that is step 3. Step 3 is to draw a deflected shape. But this shape looks something like this. Okay. Now we don't know the angle at A. We don't know. This is the tangent line. We do not know theta A. Before, when we were working with a cantilever, like we were in this case for problem 5 of the last homework, we knew that theta A here was 0, but we don't have anything we can say about theta A yet. But what we can say is that we know the change in angle from A to we know the change in angle between theta A and theta hinge. And for now, because we're only interested on the left-hand side, I'm just going to call this theta hinge. I'm not going to drop the left-hand side, but just remember that there's two thetas on either side. But yeah, we can get the change in angle. The change in angle from A to the hinge is equal to, now, do you remember that the integral of your m of x over EI is just your slope, your change in slope? And I think I've mentioned this several times now, but your m of x is equal to the integral of v of x, and your theta over theta times EI is equal to the integral of your m of x. What does this represent? Do you notice that theta x over EI, that these two are the same? If I put limits of integration here, what theta x is giving me is the change in angle from A to B. So just by finding the area of your moment diagram between 2 points, you find the change in angle between those 2 points. I don't know if that's more confusing or less confusing, but I hope that seems clear now. So this delta theta A is just the area from m over EI from A to B. Now that you need to find, you're interested in delta, you're interested in theta hinge, and you know delta theta A. You do not know what theta A itself is, but you have a relationship between these three, right? Delta theta A is equal to theta at A minus theta at the hinge. And you just need an expression for theta A in order to get theta hinge. So theta hinge is equal to theta A minus delta theta A hinge. You already have an expression for this. This goes in here. Your theta A. Now, what could you use? You can use your moment area methods here. And let's look and see what happens. Let me pull theta A outwards down here. Do you agree that I can draw a triangle from A to B? A. Let me redraw the deflected shape. And I have some tangent here. I can this tangent here. Sorry, going off screen. Okay. This tangent here. Let's call that the hypotenuse of a triangle. If I do that, then this length here is my TBA. This is the distance from the tangent at A to B at point B. And this TBA is just equal to the moment, the area moment of my moment diagram from A to B, about B. I'm like, oh, okay, but then how did I get theta A from this? Well, theta A is just, remember that if I take, this is theta A, right? This is TBA, this length is known. TBA is a length measure. It has units of length. And the distance between A and B is also units of length, it is 2L. If I take the tangent of theta A, that's opposite over adjacent, right? That equals T. Sorry, I'm not used to folding the paper in half, so my thing is starting to look a little sloppy. And then if I use a small angle approximation, like for small thetas, for small thetas, tan of theta is equal to theta. So let me bring that over here. Small angle approximation, so theta is just equal to TBA over 2L. And now I know theta A, I know delta theta A, and I can get theta hinge. I hope that did not... I think if you had questions about the topic before, about what TBA actually represents, I don't know if that actually solves anything. But yeah, stop by and see one of us. There's still a lot of time before the exam. We all have office hours before the exam again. But yeah, that's just something to keep in mind. Okay, now the next part is finding the delta at the hinge. This one's not too bad. You want to use the same exact principles. So you have this length here at point B. Well, then if I just extend, do you agree that I can just extend this out a little bit more? So let me draw the deflected shape again. This is a roller. This is a hinge. Sorry, pin. Do you agree that I can just extend out my my tangent line again? And if I extend it all the way out to the hinge, and I just bring a point down from here, this value here is T hinge, okay? And I can just do the same thing, right? I can use the same formula, equals there are several ways to do this problem. This is just one way. A to the hinge, and that'll give me the total length of here from here to here. I am only interested in, sorry, let me put this whole length is what T hinge A is, but I'm only interested in this length. I'm only interested in the displacement from the original position. And this small length is going to be where is this going to be? Sorry, I need to check the solutions really quick to make sure that I'm doing this correctly. Yeah, okay, so you know what, you actually know what this length is. Yes, let's call this delta hinge. You know that this length, because you know this angle, so you can say, well, if I know this angle and I know how far away from the angle I am, I can get this value here. So tan theta A times, is it 3L? 3L? Let's just call this Z equals Z. Then my delta is equal to T hinge A minus Z. You have Z here, you have T hinge A here. This is just the equation you need. For the last part, finding the deflection under the point load, you just use virtual work, because you only have information on this side of the hinge, so nothing you have over here will correlate over here. So you're basically doing two problems in here. And I think the easiest way to do that would be to just let losing my voice already. It's not even a review session. Would be to use virtual work here. So again, let me just draw the section that you're interested in. Where did my marker cap go? I'll keep the marker for now. The last part is here. And it goes out a little bit more. Anyway, find the moment due to this equation. Find the moment. Find big M of x. And going from 1, find little m of x. And that should be your solution. Well, not solution. You want to go for, this is your delta here is going to be equal to the integral from 0 to 2L m of x times m of x divided by EI dx. And I believe that is everything you have to do for this problem. I'm spying something a little bit different in the professor's solution, which is making me question if I did this correctly, but yeah, no, I think this is fine. I'll let you know if that turns out not to be the case, but I believe this is fine. So yeah, let us know if you have any questions. Yeah, I'll do number 2 really quick.